Right now, 4 people are training to ride a spacecraft through fire. Not metaphorically, not in a simulator. The actual vehicle, Orion, the capsule that will carry Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen on a 10-day loop around the moon, is sitting in a processing facility at Kennedy Space Center, being prepared for a mission that was supposed to have already launched. It has not launched. And the reason it has not launched is something that happened to a piece of that vehicle during its first and only uncrewed test flight. Something that was documented, published, presented to engineers, reviewed by independent boards, and then allowed to settle quietly into the background of the news cycle. Noticed mostly by specialists, absorbed by the general public in a single paragraph somewhere in the middle of a longer article about something else, and then forgotten. It should not have been forgotten. What follows is not speculation. Everything described in this investigation is confirmed by NASA engineering reports, materials science analyses, peer-reviewed literature, and public testimony before congressional committees. The data is on the record. The findings are published. The implications were stated in measured and deliberate language by the engineers and scientists whose job it is to know what happens when a spacecraft falls through the atmosphere at 25,000 miles per hour with human beings inside it. This is not a story about something going catastrophically wrong. It is a story about something going wrong in the specific, quiet, deeply technical way that precedes catastrophe. The kind of thing that, in retrospect, people point to and say, that was the moment we should have stopped and asked harder questions. That was the signal that was present. That was the finding that deserved more than a line in a press release. If you find this kind of investigation worth your time, subscribe now. The investigation begins here. In November 2022, NASA launched the most powerful rocket ever built. The Space Launch System, called SLS, stands 98 meters tall from the base of its mobile launcher to the tip of its launch abort system. Its 4 RS-25 engines, burning liquid hydrogen and liquid oxygen, produce a combined 1.6 million pounds of thrust. 2 solid rocket boosters, each approximately 54 meters long, add an additional 7.2 million pounds of thrust at liftoff. Together, the system produces approximately 8.8 million pounds of thrust in the first moments of flight. For comparison, the Saturn V, the rocket that carried Apollo astronauts to the moon between 1969 and 1972, a vehicle that remains one of the most extraordinary machines ever constructed by human beings, produced 7.6 million pounds of thrust. The SLS surpasses it. When SLS left the launch pad at Launch Complex 39B at Kennedy Space Center on the 16th of November 2022, it shook the ground for several kilometers in every direction. People standing miles from the launch site reported feeling the pressure wave in their chests. The sound arrived at the observation areas before the light reached them properly, and then both arrived together, and then the shock wave moved through the bodies of everyone watching, and the rocket climbed into the Florida night on a column of fire bright enough to cast shadows. This was Artemis I. No crew, no passengers, a shakedown flight. Sitting on top of the rocket was Orion, a capsule roughly 5 meters across at its base, built by Lockheed Martin under contract to NASA, carrying a suite of instruments, radiation monitors, thermal sensors, and a mannequin named Munikin Campos. The mannequin was seated in the commander's chair, dressed in an Orion crew survival suit, wired with sensors measuring the acceleration and vibration forces that would be experienced by a human occupant at that position. 2 additional mannequins named Helga and Zohar, one wearing a radiation protection vest, one without, occupied the remaining seats to measure the radiation environment at different points inside the capsule. The mission was to travel to the moon, enter a distant retrograde orbit around it, spend several weeks at lunar distance, and then return to Earth. A genuine shakedown, real trajectory, real distances real re-entry. 25.5 days later, on the 11th of December 2022, Orion came home. It fell through the atmosphere at 11 kilometers per second. Take that number and make it concrete. 11 kilometers per second means that in the time it takes to snap your fingers, approximately a tenth of a second, the capsule moves 1.1 kilometers. In the time it takes to read a single sentence of average length, it moves roughly 6 kilometers. At that speed, the air in front of the capsule cannot move out of the way fast enough. It does not part around the vehicle the way water parts around a ship. Instead, it compresses. It compresses so suddenly and so violently that the energy of the compression converts directly into heat. This is not friction in the conventional sense. The capsule is not rubbing against the air like a match against a striking surface. The air is being crushed against itself by the advancing capsule, and the crushing generates heat in the same way that compressing a gas in a bicycle pump makes the pump barrel warm. Except the compression is extreme beyond any ordinary comparison. The air in front of the capsule reaches temperatures of approximately 2,760 degrees Celsius. For reference, the surface of the Sun is approximately 5,500 degrees Celsius. The plasma sheath surrounding Orion during re-entry reaches roughly half the temperature of the solar surface. At those temperatures, air ceases to behave as a gas in the conventional sense. The electrons are stripped away from the nitrogen and oxygen molecules by the energy of the collision. What remains is a plasma, a fourth state of matter, distinct from solid, liquid, and gas, composed of a mixture of ions and free electrons that is electrically conductive, optically luminescent, and opaque to radio waves. This plasma sheath, glowing orange and white, surrounds the capsule completely. It blocks radio frequency transmissions. For approximately 6 minutes during the deepest and most intense part of re-entry, Orion is completely isolated. No telemetry, no voice communication, no data uplink or downlink. Mission Control in Houston can see the tracking data going dark. They can do nothing but wait. The crew on Artemis II, the actual human crew, will be on their own inside a capsule surrounded by plasma at temperatures no living thing on Earth has experienced and survived without being inside a vehicle specifically designed to survive it. That vehicle's survival depends, in the first instance, on a single component: the heat shield. On Orion, the heat shield is the circular face of the capsule, the bottom, the blunt end that faces the direction of travel during re-entry. It is approximately 5 meters in diameter. It is the largest monolithic heat shield ever flown on a crewed spacecraft. The material covering its surface is called avcoat. Avcoat is an ablative thermal protection material. Ablative means it is designed to sacrifice itself, to absorb the incoming thermal energy, undergo a chemical transformation, and release the heat back into the atmosphere in the form of ablated gases, rather than allowing the heat to conduct through to the structure behind it. The principle is similar to the way that blowing on burning wood moves the heat from the ember into the airstream, except instead of a breath of air, the medium carrying the heat away is a hypersonic plasma stream at a temperature approaching the surface of the Sun. Avcoat is not a simple material. At its most basic, it is a composite of silica fibers, essentially glass threads, embedded in an epoxy resin matrix. This composite is cast into cells shaped like a honeycomb, with each cell roughly the size of the end of a thumb. There are approximately 5,400 of these cells on the Artemis Orion heat shield. When avcoat is exposed to extreme heat, the resin component begins to pyrolyze, to chemically decompose under the action of heat, breaking down into gases and leaving behind a porous carbonized residue called char. The char is a surprisingly good thermal insulator. It is also mechanically fragile, porous and brittle compared to the original composite. But it does not need to be strong. It needs to stay in place long enough to insulate the layer of uncharred material beneath it, which then pyrolyzes in turn, generating more insulating char above it. The process propagates through the material from the hot outer surface inward, buying time for the capsule to slow down, for the plasma temperatures to drop, for the re-entry to end. The engineers knew Avcoat would ablate. They designed the heat shield for ablation. They knew the char layer would form and, in certain regions, crack and release material into the airflow. They modelled this process with sophisticated computational tools developed over decades. They validated those models against arc-jet test data, laboratory experiments in which high-powered electric arcs heat a gas stream to hypersonic temperatures and direct it at test specimens of heat shield material. They looked at the surface of previous Avcoat heat shields, including the Apollo capsules now preserved in museums, and they measured where and how material had been lost. They built a prediction of what Artemis I's heat shield would look like after re-entry. Then they saw what it actually looked like. Recovery teams reached Orion in the Pacific Ocean on the 11th of December 2022, approximately 40 minutes after splashdown. The capsule was recovered intact. The mannequins were undamaged. The instruments were functional. The mission was, by the measures that matter at the top level, a complete success. And when engineers began to examine the recovered heat shield in detail, photographing its surface, running their hands across it, measuring depths and dimensions with instruments, they found something that the models had not predicted. The ablation was not uniform. That is not surprising in itself. Ablative heat shields never ablate perfectly uniformly. The aerodynamic heating is not perfectly uniform across the surface. The material has microscopic variations. There will always be some areas that experience more ablation and some that experience less. The engineers expected non-uniformity. What they did not expect, what the photographs showed, and what the detailed measurements confirmed, was the specific nature of the non-uniformity they found. In certain regions of the heat shield, the char layer had not simply worn away gradually. It had cracked and detached in discrete pieces. Not dust, not particles, not the fine material loss that the models predicted. Actual pieces, some of them the size of a hand, had separated from the surface and been carried away by the hypersonic airflow during re-entry. The underlying virgin Avcoat in those regions, suddenly exposed, had then experienced a brief, intense direct heating event before it too began to char and insulate. The sensor data from inside the heat shield, thermocouples at multiple depths, recording temperature histories throughout the re-entry, confirmed this interpretation. At certain locations, there were temperature spikes in the data that corresponded precisely to the timing of char liberation events. A brief, sharp increase in temperature at depth, consistent with direct exposure of the underlying material, followed by a return to the expected profile as a new char layer formed. The engineers called this phenomenon char liberation. They also used terms like disbonding, char layer separation, and unexpected cracking in their technical documentation. The language is precise. None of these terms mean the heat shield failed in a catastrophic sense. The capsule survived. The structure was intact. The thermal protection performed its function in the sense that the crew compartment would have remained within survivable temperature limits, even with the observed anomalies. But the anomalies were real. They were significant. They were not predicted. And for an uncrewed mission, the margin between what happened and what would have been unacceptable was comfortable enough to absorb. For a crewed mission, the question of what the margin is, and whether the margin accounts for the full uncertainty in the models, is the question that matters most. To understand why the char liberation happened the way it did, you need to understand how the Orion Avcoat heat shield differs from the Apollo Avcoat heat shields that preceded it. Apollo also used Avcoat. The material heritage is genuine. The resin chemistry, the silica fiber reinforcement, the ablative mechanism, these are the same, but the manufacturing process is not. On Apollo, the Avcoat was manufactured by injecting the uncured resin compound directly into the honeycomb cells of the heat shield substrate, Each cell was filled with liquid avcoat, which then cured in place. The result was a heat shield in which the ablative material and the underlying structure were, in a meaningful sense, a single continuous piece. There was no separate adhesion step. There was no interface layer. The material graded continuously from the outer ablative surface to the supporting structure beneath it. For Orion, a different approach was chosen. The avcoat was cast into individual blocks outside the heat shield, allowed to cure into a solid form, and then bonded to the heat shield substrate using an adhesive. This is called the tile and bond method, and it is similar in concept to the thermal protection system used on the space shuttle, where individual silica tiles were bonded to the aluminium structure of the orbiter. The advantages of this approach are real. It is faster to manufacture, it allows damaged sections to be replaced individually, and it enables more rigorous pre-installation inspection of the ablative blocks before they are attached to the flight vehicle. But it introduces something that the Apollo process did not have: an interface. Between the cured avcoat block and the heat shield substrate beneath it, there is a layer of adhesive. That adhesive layer has its own thermal properties, its own coefficient of thermal expansion, its own response to the thermal gradient that exists during re-entry. And critically, the interface between the cured avcoat block and the substrate is a boundary, a place where two distinct materials meet, where the gas permeability changes, where the mechanical bond must resist the forces of thermal expansion and contraction and gas pressure simultaneously. During the re-entry of Artemis I, as the outer layers of the avcoat pyrolyzed and formed char, the gases generated by that pyrolysis had to travel through the char layer and escape into the airflow. This is normal. The engineers modelled it. But the rate at which those gases could travel through the char layer, the gas permeability of the char, was different from what the models assumed. The bonded avcoat blocks, manufactured by the tile and bond process, had a slightly different internal microstructure compared to the injected Apollo avcoat. The permeability was lower than the models predicted. That means the gases took longer to escape. Longer escape time means higher pressure buildup beneath the char layer. And at the specific heat rates and thermal gradients experienced during Artemis I lunar return re-entry, conditions more severe than any Apollo re-entry because Apollo used a skip entry technique to spread the heat load, while Artemis I used a direct ballistic return. The pressure exceeded the mechanical strength of the bond holding the char layer in place. The char cracked, pieces separated, they were swept away by the plasma stream. And in the regions where they separated, the surface was briefly exposed to the full intensity of the re-entry heating before a new char layer could form. The root cause analysis that followed identified these mechanisms with confidence. The permeability difference was characterized in laboratory measurements. The pressure buildup was calculated. The bond strength at the char-virgin interface was measured. The engineers constructed an updated model that could reproduce the Artemis I observations, and they used that model to predict what would happen on Artemis II. The prediction was this: char liberation will occur on Artemis II. The manufacturing modifications made to the flight heat shield, tighter curing parameters, revised adhesive specifications, enhanced bonding procedures, will reduce the magnitude and extent of the liberation compared to what would have been expected without changes. And the reduced liberation under Artemis II re-entry conditions will remain within the bounds of what the heat shield can tolerate while still performing its protective function. This is the assessment that underlies the mission certification. It is an honest assessment. The engineers are not claiming the heat shield will perform perfectly. They're claiming it will perform within acceptable limits, as defined by their best current understanding of the physics. The uncomfortable question is how much confidence that best current understanding deserves. In aerospace engineering, there is a distinction that practitioners take seriously, even though it is rarely explained to the public. It is the distinction between a model that has been validated and a model that has been calibrated. Validation means the model has made predictions that were then tested against independent observations, and the predictions were confirmed. Calibration means the model's parameters have been adjusted to match a set of observations, and then the model is used to predict future behavior. Both are valuable, but they are not the same. A calibrated model can fit the data it was calibrated to perfectly and still be wrong about the future if the calibration captured the right numerical answer for the wrong underlying physical reason. Engineers call this tuning to the data, and they are generally cautious about it because a model tuned to one dataset may not transfer cleanly to a different set of conditions. The updated AVCOAT ablation models used for Artemis II certification were calibrated against the Artemis I flight data. They were then applied to predict Artemis II behavior. This is the standard approach when you have one flight of data and need to certify a second flight. It is defensible. It is what the available evidence supports. But it is calibration, not independent validation. The models have not been tested against an Artemis II flight and confirmed. They are predicting an Artemis II flight from an Artemis I calibration. That is a meaningful distinction, and it is one that some of the engineers involved in the review process noted explicitly in their technical communications. The non-trivial uncertainty that appears in the independent review documentation is the quantitative reflection of this distinction. When the reviewers write that model uncertainty remains non-trivial, they are saying the confidence interval around our prediction of Artemis II heat shield performance is wider than we would like, because we have one calibration flight and cannot independently validate the models before the second flight. That is not a reason not to fly. It is a reason to be precise in public about what is and is not known. The public communications around Artemis II have not been precise in that way. The narrative has been one of resolution, problem found, investigation conducted, root cause identified, fix implemented, vehicle certified. Each of those statements is accurate. Together, they produce an impression of a problem that has been solved. The non-trivial uncertainty, the calibration versus validation distinction, the thin margin between acceptable and unacceptable desponding. These are present in the technical record. They are absent from the public record. Now consider what happened with the life support system. The environmental control and life support system on Orion, designated ECLSS, is responsible for maintaining the atmosphere inside the crew module. It controls the partial pressure of oxygen, removes carbon dioxide exhaled by the crew, manages humidity, regulates temperature, and monitors cabin pressure for leaks. It is, in the simplest possible terms, the system that keeps the crew alive when they are not on Earth. Every breath they take inside Orion is breath that ECLSS has prepared for them. For Artemis I, the ECLSS operated in an automated mode, maintaining the cabin environment without human intervention and without the metabolic loads, the breathing, the body heat, the humidity that a living crew would add. The system's performance during Artemis I was monitored in real time from the ground. The data was archived. After the mission, engineers analysed it in detail. What they found was that several ECLSS subsystems performed differently than their models had predicted. The carbon dioxide scrubbing system, which uses a chemical sorbent to capture exhaled CO2 before it can build up to harmful concentrations, showed different efficiency characteristics in certain operational modes than the pre-flight analysis had assumed. The thermal control subsystem, which manages heat rejection from the crew module, showed unexpected behaviour during the transition between mission phases. These were not emergency-level failures. The system maintained the cabin environment within acceptable limits throughout the mission. But the differences between prediction and observation were large enough to require investigation. The ECLSS investigation followed the same pattern as the heat shield investigation. Root causes were identified. The carbon dioxide scrubbing anomaly was traced to a flow distribution issue in the sorbent beds that was sensitive to the specific operating pressure and temperature conditions of the mission. The thermal control anomaly was traced to an interaction between two subsystems that the models had not fully captured. Engineering changes were designed and implemented. Ground testing was conducted. The changes were validated against the test data. And again, the ground testing showed that the systems performed differently from the original predictions. Not catastrophically, not unacceptably, but differently. The root causes were understood. The engineering changes helped. The performance was within the certified range. Two major systems, two sets of anomalies, two investigations, two sets of manufacturing and design changes, two sets of ground test validations showing improved but imperfect agreement with the updated models. This is the pattern of a vehicle that is being understood through flight, which is normal, and has always been normal, and was normal for every vehicle in the history of human spaceflight, from Mercury through the Space Shuttle. No vehicle has ever flown its first crewed mission with perfect model agreement across all systems. The models are always an approximation of reality. The flights teach you where the approximations fall short. The question that is not being asked in the public narrative is, given that the vehicle has taught us something important on its first flight, and given that the second flight carries people, how much of what we have been taught should we be saying out loud? There are 4 people whose lives depend on the answers to these questions. They have names, they have families, they have decades of professional training and genuine understanding of the risks they are accepting. They are not naive and they are not uninformed. The astronaut office at NASA receives detailed technical briefings on vehicle performance. The crew members of Artemis II have almost certainly seen the engineering documentation in more detail than anything discussed here. They have made their own assessments. But the public, the people paying for the program, the people watching the launch, the children who will see the news coverage and decide in that moment whether they want to grow up to be astronauts, the public deserves an honest account of what certified for flight means when the models were wrong on the first flight and better on the second, but still non-trivially uncertain. This deserves more than a press release. There is a history to this kind of communication failure, and it is worth understanding in some detail, because the mechanisms are not unique to NASA and not unique to spaceflight. They are features of how large institutions communicate risk under conditions of schedule pressure, political scrutiny, and public expectation. On January 28, 1986, Space Shuttle Challenger broke apart 73 seconds after launch, killing all 7 crew members. The immediate cause was the failure of an O-ring seal in the joint between 2 segments of the right solid rocket booster. Cold temperatures on the morning of the launch had stiffened the O-ring material, reducing its ability to seal the joint. Hot combustion gas escaped through the breach, burned through the external tank, and triggered a structural failure that destroyed the vehicle. The O-ring concern was not unknown. Engineers at Morton Thiokol, the manufacturer of the solid rocket boosters, had been aware of O-ring erosion and anomalies for years. They had documented the anomalies, they had raised concerns. The concern had been discussed in internal meetings, and flight by flight, as the shuttle flew successfully despite the O-ring anomalies, the anomalies were reclassified from alarming to acceptable. Not through any single decision, not through any dishonest act, through the accumulation of successful flights, each of which seemed to provide evidence that the anomalies, while present, were not critical. This is what the sociologist Diane Vaughan called normalization of deviance. The deviation from expected performance, the O-ring erosion, was over time incorporated into the expected performance. It became normal. And when it became normal, the decision to launch on a cold morning in January felt to the people making it like a reasonable extension of what had always been acceptable. The Rogers Commission, established to investigate the Challenger accident, found that the information necessary to understand the risk had been available within the organisation. It had been generated, documented, and transmitted. What had failed was the process by which that information was integrated into decision-making. The warning signals had been present. They had been absorbed into a decision framework that had been calibrated by years of successful flights. And in that framework, they did not look like warnings. They looked like data points in a distribution that had always resolved in the vehicle's favour. NASA spent years after Challenger rebuilding its safety culture. The changes were real and substantive: an independent safety office, enhanced anomaly tracking systems, formal requirements for anomaly resolution before return to flight. A culture that, at least in its stated values, placed safety above schedule. And then, 17 years later, Columbia happened. Space Shuttle Columbia broke apart during re-entry on February 1st, 2003, killing all 7 crew members. The immediate cause was a breach in the thermal protection system on the left wing, caused by a piece of foam insulation that had detached from the external tank during launch and struck the leading edge of the wing at high velocity. The leading edge panels were made of reinforced carbon-carbon, a high-temperature material capable of withstanding re-entry heating. The foam strike had damaged one of those panels. During re-entry, hot gas penetrated through the damaged panel, destroyed the wing structure, and caused the vehicle to lose control. Again, the foam shedding was not unknown. Foam had been observed detaching from the external tank on previous shuttle flights. It had been documented. It had been analysed. And flight by flight, as the shuttle flew successfully despite the foam strikes, the foam shedding had been incorporated into the acceptable performance range of the vehicle. The Columbia Accident Investigation Board, examining the accident, found the same pattern that the Rogers Commission had found after Challenger. Information that should have been alarming had been processed through an institutional framework calibrated by success, and had emerged from that processing as routine. The board's report introduced a phrase that has been central to NASA safety discussions ever since. It noted that NASA had, over time, allowed foam strikes to migrate from the category of concerns requiring resolution to the category of accepted risk. The migration happened gradually, without any single deliberate decision. It happened because the flights kept succeeding, and successful flights are evidence of a kind that the vehicle can tolerate the deviation. The evidence is always insufficient until the moment it is not. What does this history mean for Artemis II? It does not mean the mission will fail. The base rate of a catastrophic failure on human spaceflight missions, even accounting for Challenger and Columbia, is low. The history of spaceflight includes far more successes than failures. The engineering on Artemis is more sophisticated than the engineering on Apollo, and Apollo succeeded repeatedly. The root cause investigation for the heat shield anomaly was genuine and thorough. The engineers working on this problem are not careless. What the history means is that the specific institutional mechanisms by which safety concerns get quietly absorbed, normalization of deviance, the weight of previous success, the translation of nuanced uncertainty into clean public narratives, are not unique to any particular program or era. They are properties of the environment in which large aerospace programs operate. They do not require bad intentions. They do not require dishonesty. They require only the ordinary pressures of schedule, budget, political expectation, and the professional optimism that is, in some measure, necessary to do this kind of work at all, and the specific signal to watch for, the signal that those mechanisms may be operating, is the gap between what the technical documentation says and what the public communications say. The gap is not always a warning. Sometimes it is just the routine simplification that makes complex technical content accessible to a general audience. But when the technical documentation contains phrases like non-trivial uncertainty and calibration against limited flight data and margins that do not provide comfortable buffer, and the public communication contains phrases like heat shield certified and investigation complete and root cause resolved, the gap is worth examining. The gap exists on Artemis II. Now let us be precise, because precision matters in both directions, and the goal here is not alarm but understanding. The Artemis II heat shield is the most thoroughly tested Orion heat shield that has ever been produced. The investigation that followed the Artemis I anomaly involved materials scientists from multiple universities, national laboratories, and NASA centers. It involved arc-jet test campaigns at the Ames Research Center in California, one of the few facilities in the world capable of generating the heat fluxes relevant to lunar return re-entry. It involved high-fidelity computational fluid dynamics modeling on some of the most powerful computers available to the aerospace community. It involved independent review by engineers from outside the Artemis program who had no institutional stake in the outcome. The Artemis II heat shield has undergone manufacturing modifications that directly address the root cause of the Artemis I anomaly. The curing process changes reduce the void content within the avcoat material, reducing the gas pressure that builds beneath the char layer. The bonding process improvements reduce the variability of the adhesive interface, reducing the probability of localized disbond initiation. The inspection enhancements identify pre-existing defects in the delivered heat shield and allow their removal before flight. The arc-jet testing that validated these changes showed improved performance. The disbonding still occurred because the underlying physics still applies, but it occurred at a reduced magnitude and over a smaller area of the test specimens. The updated models, incorporating the calibrated root cause physics, accurately predicted the improved but imperfect performance. The engineering assessment is that the Artemis II heat shield, under its expected re-entry conditions, will experience char liberation within margins that the heat shield can accommodate while continuing to protect the crew compartment. This assessment was reviewed by the NASA Engineering and Safety Center, by the Mission Safety Review Process, by the Program Requirements Control Board, and by independent technical authority representatives. None of these reviews identified the heat shield as a program stopper. None of them recommended that the mission be grounded pending additional development testing. They identified the residual uncertainty, documented it, and found it acceptable for flight. These reviews are not perfunctory. The people who conduct them are serious professionals. They push back. They ask hard questions. They require documented answers. They are not rubber stamps, and they cleared the mission. This is the full complexity of the situation. A real anomaly, a genuine and thorough investigation, real engineering improvements, residual uncertainty that is documented and non-trivial, and a professional assessment by qualified people that the residual uncertainty is within acceptable bounds for a crewed mission. Not no risk, not zero uncertainty. Acceptable risk as evaluated by the people whose job it is to make that evaluation. The question the public has not been asked to engage with is, what does acceptable mean in this context? And who decided? In human spaceflight, acceptable risk is defined by two things: the magnitude of the risk and the value of the mission. A risk that would be unacceptable for a routine transportation flight might be acceptable for a pioneering mission that establishes crucial scientific and operational knowledge. A risk that would be unacceptable if other options were available might be acceptable if the only alternative is not going at all. The Artemis program is not a routine transportation flight. It is an attempt to return humans to the moon for the first time in more than half a century. to establish the operational foundation for a sustained lunar presence and to advance the human species' ability to operate beyond the Earth-Moon system. The people managing that program have concluded that the residual uncertainty in the heat shield models does not exceed the acceptable risk threshold for a mission of this importance. They may be right. They may also, in the way that institutional cultures operating under sustained pressure can be wrong without knowing it, be applying a threshold that has been quietly recalibrated by years of schedule slippage, budget overruns, and political expectations about when humans will return to the moon. It is not possible to know from outside the program which of these is true. What is possible is to name the question, to describe the evidence that gives rise to it, and to note that the public narrative around Artemis II has not named it. The specific finding that was quietly ignored is this: the Orion heat shield, as manufactured and certified for Artemis II, is known to produce char liberation events during lunar return re-entry. The magnitude and distribution of those events is predicted by models calibrated against a single flight of data. The calibrated models show the events will be within acceptable limits. The confidence interval around those predictions is non-trivial. The margin between the predicted performance and the threshold of structural significance is positive, but not comfortable. And all of this is documented in the technical record and absent from the public narrative. Reed Wiseman will sit in the commander's seat. He is 54 years old. He was selected as a NASA astronaut in 2009 and flew his first mission to the International Space Station in 2014. He served as chief of the astronaut office from 2020 to 2023. He knows what he is sitting in. He has read the engineering documentation. He has asked the hard questions. Victor Glover will sit in the pilot's seat. He is 48 years old. He flew on the first operational crewed Dragon flight to the ISS in 2020 and spent 6 months aboard the station. He holds a master's degree in flight test engineering. He understands flight test. He understands what it means to fly something that has not been fully characterized. Christina Koch will sit in the mission specialist seat. She is 46 years old. She holds a master's degree in electrical engineering and has a background in applied physics. She spent 328 consecutive days aboard the International Space Station, the longest single spaceflight by a woman in history. She has spent more time in orbit than almost any American astronaut alive. Jeremy Hansen will occupy the fourth seat. He is 48 years old. He is a colonel in the Royal Canadian Air Force and a Canadian Space Agency astronaut selected in 2009. He has not yet flown in space. Artemis II will be his first spaceflight, and it will not be a gentle introduction to orbital mechanics. It will be a trip to lunar distance and back inside a spacecraft that the engineering record describes as having non-trivial uncertainty in its thermal protection performance. These 4 people have chosen this. They would not have it otherwise. And yet, the public that will watch their launch, the parents who will take their children to see it on television, the legislators who vote to fund the program, the future astronauts who are now in school thinking about whether to pursue this kind of career, they have not been given a fair account of what the technical record contains. The narrative they have been given is one of resolution. The technical record contains something more complicated and more honest. After the mission, after Orion falls through the atmosphere again, this time with 4 people inside it, this time with the heat shield experiencing the physics that the models predict and producing the char liberation that the ArcJet tests confirmed and the disbonding that the updated analysis bounds. The sensor suite embedded throughout the heat shield will have recorded the complete thermal history of the entry. Those sensors will capture temperature profiles at multiple depths, at multiple locations across the heat shield surface. They will record the moment-by-moment progression of the ablation front through the material. They will record the temperature spikes associated with char liberation events, the same kind of spikes that the Artemis I data showed, which allowed the root cause investigation to reconstruct the mechanism. After recovery, after the crew has been extracted and the capsule has been transported to the processing facility, the engineering team will go over every centimetre of the heat shield surface. They will photograph it. They will measure it. They will compare the observed ablation pattern to the model predictions. They will find, with very high probability, some differences. Some places where the desponding was larger than the model predicted, and some where it was smaller. They will begin a new round of model calibration, incorporating the Artemis II flight data. The models will be better. The predictions for Artemis III will be more confident. This is how it works. This is how it has always worked. The knowledge grows flight by flight. The uncertainty shrinks incrementally. At some point in the future, after enough flights and enough model refinements and enough accumulation of thermal sensor data, the predictions will be good enough that aerospace engineers use phrases like high confidence without the qualifier of non-trivial residual uncertainty. That point has not yet been reached. It is also worth knowing that the heat shield is not the only thing standing between the crew and the energy of re-entry. The capsule itself, its structure, its thermal blankets, its internal insulation, provides layers of protection beyond the primary ablative shield. The re-entry profile for Artemis II is designed to manage the heat rate within limits that the heat shield is certified to handle. The parachute system, the flotation systems, the recovery operations, all of these are the layered defences that together define the overall safety of the mission. The heat shield is one layer, albeit the most critical one during the entry phase, but it is the layer about which the most was discovered on the first flight. And it is the layer about which the most uncertainty remains for the second flight. And it is the layer about which the public has been told the least. Before examining what comes next, it is worth pausing to look carefully at how the specific arc jet testing for Artemis II was conducted, because the details of those tests illuminate the distance between testing and flight in ways that matter. Arc jet testing is the primary tool available to aerospace engineers for evaluating ablative heat shield performance in conditions that approximate hypersonic re-entry. The principle is straightforward. Pass a large electrical current through a gas stream, generating an arc that heats the gas to plasma temperatures, and direct that hot gas at a test specimen of heat shield material. The facility most relevant to the Artemis program is located at the NASA Ames Research Center in Mountain View, California. The Ames ArcJet complex includes several separate test legs, each capable of generating different combinations of heat flux and pressure. For lunar return re-entry testing, the aerodynamic heating facility and the panel test facility were the primary workhorses. The heat fluxes achievable in ArcJet testing, measured in watts per square centimetre, can reach into the hundreds. The surface temperatures on test specimens can reach well above 2,000 degrees Celsius. By those measures, ArcJet facilities are extraordinarily capable. They are the closest thing available to the re-entry environment without actually performing a re-entry. But they are not re-entry, they are approximations of re-entry, and the approximations have known limitations. The most significant limitation is spatial scale. An ArcJet facility can expose a test specimen of perhaps 30 centimeters across to high heating. The Orion heat shield is 5 meters across. The flow conditions on a real heat shield, the way the boundary layer develops over the full 5-meter span, the pressure distributions across the curved surface, the interaction between the hot plasma and the ablating material over a large area cannot be replicated by exposing a small coupon to an ArcJet stream. The engineers compensate for this by testing multiple specimens at multiple heating conditions, mapping out the response of the material across the range of conditions that different parts of the heat shield surface experience. But the integrated behavior of the full heat shield, the interaction between adjacent regions, the lateral flow of ablation products, the development of the ablation pattern over the full surface simultaneously is not directly tested, it is modelled. The second significant limitation is duration and trajectory. A real lunar return re-entry lasts approximately 11 minutes from entry interface to peak deceleration. The heat rate is not constant. It rises to a peak and then falls as the vehicle decelerates. The material in the heat shield experiences a time-varying thermal input that drives the ablation front through its depth in a specific way. Arc jet testing can replicate portions of this trajectory, but replicating the full 11-minute profile at the relevant heat fluxes requires large amounts of arc jet time, which is expensive and limited. The test campaigns conducted for Artemis II certification exposed specimens to carefully selected conditions meant to capture the critical portions of the re-entry thermal history. But the full temporal evolution of the ablation process, as it would occur during an actual flight, was not directly reproduced. The third limitation is the mechanical environment. During re-entry, the capsule is decelerating at forces up to several times the acceleration due to gravity. The ablating material is simultaneously experiencing high temperatures and significant mechanical loads. Arc jet tests are conducted with the specimen stationary. The combined thermal and mechanical loading that the heat shield experiences during flight is not replicated by the testing. These limitations are not secrets. They are well known to everyone involved in heat shield development. The engineering community has worked for decades to understand how to use arc jet data intelligently, with appropriate corrections for the differences between test conditions and flight conditions. The models that translate arc jet results into flight predictions are themselves sophisticated tools with documented uncertainty. The point is not that arc jet testing is unreliable. The point is that the chain from arc jet specimen to full-scale flight heat shield performance involves multiple modelling steps, each of which introduces uncertainty, and the accumulated uncertainty across that chain is what the engineers describe as non-trivial. There is a concept in engineering analysis called the test and analysis cycle. The idea is that you test at a scale you can afford, build models that predict the test results, extend those models to the full-scale flight environment, and certify based on the combined confidence from test data and model predictions. The quality of the certification depends critically on how well the models that bridge the gap between test and flight conditions have been validated. For a new vehicle or a new anomaly, like the Orion Heat Shield Char Liberation, the models bridging that gap are doing so without prior flight validation at the full-scale condition. They are being validated against the test data, and then they are being extended to the flight environment on the basis of physical principles and engineering judgment. The Artemis II certification rests on this structure. The ArcJet tests validated the updated ablation models at specimen scale. The validated models were extended to the full heat shield. The full heat shield model predictions were compared to the one available flight data point, the Artemis I thermal sensor data, and found to be in improved agreement with the updated physics. And then the same models were used to predict Artemis II performance. This is good engineering. It is also engineering with inherent uncertainty, and the magnitude of that uncertainty is larger than it would be if there were multiple calibration flights, or if ArcJet testing could perfectly replicate flight conditions, or if the models had been independently validated against a third dataset that was neither the calibration source nor the application target. Understanding this structure, the test and analysis cycle, the model validation limitations, the chain of inference from specimen to flight, is what distinguishes an informed assessment of the heat shield has been certified from the public impression that the heat shield has been fixed and tested and proven safe. Both statements can be simultaneously true in their own registers. The engineering community lives in the first register. The public narrative presents the second. The distance between them is not deception. It is the ordinary compression of technical content into communicable messages. But when the compressed message concerns the safety of people, the compression deserves scrutiny. Consider now the timeline of events, because the sequence matters and illuminates how the communication gap developed. November 16th, 2022, Artemis I launches. December 11th, 2022, Orion splashes down in the Pacific. Recovery teams document the heat shield. January 2023, initial engineering reports on the heat shield anomaly begin circulating within the program. The char liberation findings are confirmed. A root cause investigation is formally initiated. March 2023, NASA holds a public briefing on the Artemis I mission results. The heat shield anomaly is mentioned. It is described as a finding under investigation. The briefing is framed around the overall success of the mission. The anomaly receives approximately the same emphasis as several other findings from the mission, a fraction of the total briefing time, a few paragraphs in the written summary. The coverage of that briefing in major newspapers and science outlets focuses primarily on the mission's achievements, the performance of the SLS, the behavior of the Orion systems, the radiation data from the mannequins. The heat shield anomaly is mentioned in some coverage, typically in a paragraph toward the end of articles that lead with success. By the following week, it is not in the news at all. Throughout 2023, the root cause investigation continues. ArcJet testing campaigns are conducted. Materials characterization work progresses at Ames and at Lockheed Martin facilities. The investigation is staffed by hundreds of engineers and produces thousands of pages of documentation. November 2023, NASA publicly confirms that Artemis II will be delayed from its previously planned date. The reason given includes the ongoing heat shield evaluation. This is the moment at which a thorough investigation of the anomaly's significance should have been warranted in mainstream coverage. Instead, the delay story is framed primarily around schedule and cost, familiar themes for the Artemis program, which has been subject to delays and cost growth throughout its existence. The heat shield is mentioned, but the specific nature of the finding, what char liberation means, what the models show, what the uncertainty is not explained. Early 2024, NASA announces a further delay, moving the earliest possible Artemis II launch from late 2024 to no earlier than September 2025. Multiple factors are cited. The heat shield investigation is listed alongside life support system work and other schedule items. By now, it is being treated in public communications as one issue among many, rather than the primary technical uncertainty driving the delay. Throughout 2024 and into 2025, the ArcJet validation campaigns are completed. The manufacturing modifications for the Artemis II flight heat shield are implemented and inspected. The certification analysis is completed. Independent reviews are conducted and concluded. The heat shield is certified for flight. The public record of this sequence, assembled from press releases, briefing transcripts, and news coverage, presents a story of methodical problem solving. The investigation is conducted. The answer is found. The fix is implemented. The vehicle is certified. The narrative has a clear shape: challenge, response, resolution. What the narrative does not show, what requires reading the technical documents to understand, is that the resolution at the end of that sequence carries a qualifier. The qualifier is non-trivial uncertainty. The qualifier is calibrated but not validated models. The qualifier is margins that are positive but not comfortable. And the qualifier was present in the technical documentation throughout the sequence, noted by the engineers, reviewed by the independent boards, and consistently absent from the public-facing version of the story. The absence of the qualifier is not unique to this program. It is, in fact, the normal condition of public science and engineering communication. Technical uncertainty is difficult to communicate accurately without losing the audience. Non-trivial model uncertainty sounds, to a non-technical audience, either like nothing or like everything, either like normal scientific hedging that can be ignored, or like a smoking gun that the mission should be cancelled. Neither interpretation is accurate. The accurate interpretation requires a framework for understanding what non-trivial means in engineering risk assessment, a framework that most people do not have and that press releases cannot provide. But the consequence of this communication failure, repeated across enough programs and enough missions, is an accumulated public misunderstanding of what human spaceflight actually is. The public understands human spaceflight through its successes, communicated as achievements, and its failures, communicated as tragedies. It does not understand human spaceflight through the permanent, ongoing, quietly documented gap between what the engineers know and what the physics will do. That gap is the actual texture of the work. It is the environment in which every decision is made. And it is essentially invisible to everyone outside the engineering community because the communications architecture of large aerospace programs is not designed to make it visible. There is one more piece of this story, and it involves an analogy that the engineers themselves use. In thermal protection engineering, there is a concept called the ablation margin, the additional thickness of heat shield material above what the thermal analysis predicts will be consumed during re-entry. The ablation margin exists to account for uncertainty. If the thermal analysis is wrong, if the actual heating is higher than predicted, or if the material ablates faster than the model suggests, the ablation margin provides an additional buffer before the heat shield would fail to protect the structure. Think of it like the margin of safety in a bridge. A bridge designed to support 10,000 pounds of load might actually be built to withstand 30,000 pounds, a factor of 3 safety margin. If the actual load on the bridge turns out to be 12,000 pounds instead of the predicted 10,000, the bridge still stands. The margin absorbed the error. For ablative heat shields, the margin is expressed as the difference between the predicted char depth and the total thickness of the heat shield material. If the heat shield is 10 centimeters thick and the analysis predicts the char front will consume 6 centimeters during re-entry, the remaining 4 centimeters is the margin. If the actual char depth turns out to be 7 or 8 centimeters because the heating was higher than predicted or the ablation rate was faster, the heat shield may still function. At 9 or 10 centimeters, it fails. The char liberation anomaly on Artemis I complicates this simple picture. When pieces of char separate from the surface, the local ablation profile at that location is no longer smooth. The virgin material beneath the separated char is suddenly exposed to direct heating. It chars more rapidly than the surrounding material, creating a deeper local ablation at the liberation site. The models that predict the local ablation depth at liberation sites are the most uncertain part of the updated analysis because the physics of what happens when char separates and the underlying material is suddenly exposed to full heating is complex and depends on the size and timing of the liberation event, both of which are themselves uncertain. The ablation margin for the Artemis II heat shield, accounting for the predicted char liberation events and their local deepening effect, remains positive in the engineering models. There is still margin. The models say the char front will not consume the full thickness of the heat shield at any location during Artemis II re-entry. But the magnitude of the remaining margin, how much buffer exists between the predicted worst-case local ablation depth and the total heat shield thickness, is the number that the independent reviewers were examining when they wrote non-trivial uncertainty. That number has not been disclosed publicly to the knowledge of this investigation. The engineering documents that contain it are either proprietary or classified as sensitive program information. What is publicly known is that the margin exists, that it is positive, and that the confidence interval around the prediction of its magnitude is non-trivial. Whether the margin is comfortable, whether a person who understood what the number meant would feel reassured or merely not alarmed, is a question that the public record does not answer. The engineers know the number, the program managers know the number, the independent reviewers know the number, the crew members presumably know the number or have been briefed on its significance. The public does not know the number, and the public framing of the certification, the heat shield has been certified for flight, does not convey anything about the number's magnitude or about the confidence interval surrounding it. This is what was quietly ignored. Not a single dramatic moment, not a single decision, a systematic, institutional, entirely ordinary process by which technical nuance does not survive translation into public communication, and by which the qualifier, non-trivial, uncertainty, thin margin, calibrated models, settles into technical documents, while the clean narrative of resolution rises to the surface and becomes the public story. In all probability, it will succeed. In all probability, the heat shield will char and ablate and lose some material and remain intact enough to protect the crew compartment for the duration of the entry. But before accepting all probability as the final word, consider the political and institutional pressures that shape what large aerospace programs say about themselves, and how those pressures have shaped the Artemis II narrative specifically. The Artemis program has been in development in various configurations and under various names since the end of the Space Shuttle program. The Constellation program, the original post-shuttle lunar return effort, was cancelled in 2010, having spent approximately $9 billion without reaching flight. Its replacement, the Space Launch System, was authorized by Congress in 2010 and has been in development ever since. As of the Artemis I launch in November 2022, the cumulative investment in SLS and the Orion spacecraft exceeded $23 billion. By the time Artemis II launches, that number will be larger. This investment creates a political environment in which the program cannot afford to be seen as failing, or even as experiencing serious technical setbacks. Not because anyone has made a corrupt decision to prioritize appearances over safety, but because the institutional incentives of large government-funded programs push in a particular direction. The program needs continued political support. Political support is easier to maintain when the news is good, when the news is technically nuanced, when the accurate statement is that the heat shield experienced an anomaly that is now better understood, with residual non-trivial uncertainty within certified margins that are positive but not comfortable. The political pressure is toward simplification, toward the version that sounds like resolution, toward the version that does not give critics of the program another line of attack and does not generate coverage that might prompt budget hearings. This is not unique to NASA. It applies to any large program in any domain: defense acquisition, nuclear power, pharmaceutical development, where technical complexity is high, public understanding is low, political scrutiny is real, and the institutional stakes are significant. The mechanisms by which accurate technical nuance gets simplified into clean public narratives are not a feature of bad institutions. They're a feature of institutions operating in an ordinary political and media environment. What distinguishes human spaceflight from most other domains is the specific consequence of the simplification. When a bridge is certified with non-trivial model uncertainty and the public is not told, the bridge may stand for decades. When a pharmaceutical is approved with residual uncertainty about its interaction effects, the patients may never experience the interaction. But when a spacecraft heat shield is certified with non-trivial model uncertainty and the uncertainty resolves in the wrong direction, the consequence is immediate, total, and irreversible. There is a useful comparison available from a program running in parallel with Artemis. Boeing's Starliner spacecraft was developed under NASA's Commercial Crew Program to carry astronauts to the International Space Station. In June 2024, Starliner finally carried 2 NASA astronauts, Butch Wilmore and Suni Williams, to the ISS for what was planned as a brief demonstration mission. During the approach, several reaction control thrusters failed and helium leaks were detected in the propulsion system. NASA spent months evaluating whether the technical anomalies posed an unacceptable risk for the crewed return. The deliberations were more visible to the public than is typical for aerospace technical debates. Eventually, NASA decided the risk was too high. Wilmore and Williams returned on a SpaceX Dragon 9 months later. The Starliner situation is instructive because the technical debate became visible enough to generate sustained public attention and ultimately a high-profile decision that prioritized technical caution over schedule and institutional pressure. The heat shield situation was not visible in the same way, not because it was less technically significant, but because the communication pattern followed the ordinary institutional script. The visibility of the Starliner situation was an exception, driven by the unusual circumstance of a crew being aboard the station while the debate proceeded. The heat shield situation followed the rule. The rule produces clean public narratives. The exception produces visible technical debates. When human lives are at stake, the exception may better serve the public interest, not because it changes the outcome, but because it creates accountability, because it makes the decision-making visible, and because it ensures that if the worst happens, the public record shows that the uncertainty was known and weighed rather than absorbed into institutional optimism. Consider, finally, what the crew themselves know and how they process it. Astronauts are not naive about risk. They are among the most risk-literate people in the world, with technical backgrounds in engineering, science, or medicine. Many with flight test experience that gives them an especially calibrated sense of how vehicles behave at the frontier of their performance envelopes. They have spent their careers thinking about what failure modes look like, how to detect them, how to respond. They have access to technical information that the public does not receive. The astronaut office maintains direct channels to the engineering teams. Crew members preparing for a mission participate in detailed design and safety reviews. What is interesting is not whether the Artemis II crew knows about the heat shield uncertainty. They almost certainly do. What is interesting is the framework within which they process it. Professional risk-takers develop, by necessity, a framework for coexisting with non-trivial uncertainty. A test pilot who cannot fly an aircraft with residual uncertainty about its performance envelope cannot do their job. An astronaut who cannot commit to a mission with incompletely validated systems cannot serve. The professional norm is to assess the risk rigorously. Satisfy yourself that the residual uncertainty is within acceptable bounds, as defined by the best available analysis, and then set the uncertainty aside and focus on the mission. This is the right framework for the people doing the job. It is not necessarily the right framework for the public discussion about whether the job should be done under those conditions at this point in the program's development. The crew's professional acceptance of the risk does not resolve the institutional communication question. Both things can be true simultaneously. The crew can understand and accept the risk, and the public can be given an honest account of what that risk consists of. What the current communication pattern produces is only the first half. The crew's bravery is acknowledged and admired. The technical nature of what they are being brave about is smoothed into resolution narrative before it reaches the general public. That smoothing is a process, not a conspiracy. And the process, when applied to human spaceflight, has a documented history of producing outcomes that the people inside the institutions did not intend and could not see coming, because the smoothing made the uncertainty invisible before the physics had a chance to demonstrate whether it was benign. The mission will launch. In all probability, Reed Wiseman will splash down in the Pacific Ocean alive, and so will Victor Glover, and so will Christina Koch, and so will Jeremy Hansen, and there will be celebrations in Houston and Washington and Ottawa, and children watching on screens will decide they want to be astronauts. All of that is likely, and it is compatible with everything said here. What is not compatible with everything said here is a public narrative in which the Artemis II heat shield is described as a solved problem. It is not a solved problem, it is a better understood problem with a well-characterized mechanism, a calibrated model, manufacturing improvements that reduce the magnitude of the anomaly, and residual uncertainty that is non-trivial and honestly documented in the engineering record. The distinction matters not because the mission should not fly, it should. It matters because the culture of human spaceflight, the safety culture that was rebuilt after Challenger, rebuilt again after Columbia, and now has to survive the particular pressures of the Artemis program, depends on that distinction being maintained. It depends on anomalies remaining anomalies. It depends on non-trivial uncertainty remaining non-trivial. It depends on the gap between the model and the reality being named and held open and not allowed to quietly close in the public narrative, just because schedule pressures and political expectations and professional optimism make it more comfortable to say resolved than to say better understood but still uncertain. Right now, the heat shield is attached to the capsule. The capsule is in the processing facility. The crew is training. The rocket is being assembled. The launch date approaches. And in the technical record, quietly, the words non-trivial uncertainty sit in a document that most people will never read, in a section that describes the engineering confidence in the system that will protect 4 human beings from the temperatures of a plasma stream at the edge of what the atmosphere can produce. That is the thing that was quietly ignored. Not because the engineers were not honest, they were. Not because the safety reviewers were not diligent, they were. Because the architecture of large program communication tends to produce resolution narratives, and resolution narratives leave residual uncertainty in the footnotes. And most people never read footnotes, and the public discourse around human spaceflight rarely goes below the press release level. And a single paragraph about a heat shield investigation buried in a longer article about schedule delays does not convey what the words non-trivial uncertainty mean to the engineers who wrote them. It means we are less certain than we would like to be. We have done everything we can with the knowledge available to us. We have reduced the uncertainty as far as the tools and data allow, and there is still a gap between the model and the reality that we cannot close before this flight. We are proceeding because the gap, as we understand it, is within acceptable limits, and we are documenting that the gap exists and that the limits are the best estimates available, and that this is what it means to go somewhere that no one has gone before, with the tools and knowledge that exist right now in this moment in history. That is the honest statement. It is in the documents. It is not in the press releases. The 4 people in that capsule are going to the moon and back. They will be suspended at their greatest distance from Earth, approximately 400,000 kilometers from the nearest other human being. The distance from the surface of the moon to the surface of the Earth, the actual physical gap, expressed in kilometers, is 400,000. Light takes approximately 1.3 seconds to cross it. A radio signal carrying a voice takes the same. If anything goes wrong at that distance, there is no rescue. There is no abort option that brings them home in hours rather than days. The vehicle must work. The heat shield must work. The life support must work. The navigation must work. The parachutes must work. All of it must work in sequence over 10 days in an environment where the nearest human assistance is a journey measured in days even if launched immediately. This is the context in which non-trivial uncertainty in the heat shield model must be understood. Not as a crisis, not as a reason not to go, as the specific, technical, honestly documented gap between what we know and what we need to rely on. As the remainder, the thing that is left over after all the engineering has been done, and all the testing has been conducted, and all the reviews have been held, and all the analyses have been completed. The residual that remains, because the knowledge of how plasma interacts with ablating ceramic composites at lunar return velocities is not yet, and may never be, perfect. There is something worth knowing about the specific people who built the knowledge the program is now relying on. The materials scientists who characterized the Avcoat permeability and identified the root cause of the char liberation are, in most cases, people who have spent their entire careers studying the way extreme heat interacts with structured composite materials. They work in a niche so specialized that there are perhaps a few hundred researchers in the world with deep expertise in ablative thermal protection systems for human spaceflight. Many of them have spent time at NASA Artemis, or at the Johnson Space Center Materials Laboratory, or at the academic groups that historically supplied the aerospace industry with ablation physics. They do not make news. Their names do not appear in press releases. Their work happens in laboratory environments and in the pages of journals read by a few thousand specialists globally. These are the people who found the root cause. When the char liberation was observed on Artemis I, it was their existing body of work, decades of theory, test data, and model development that provided the vocabulary and the tools to understand what had happened. The permeability mechanism they identified was not invented for the occasion. It was drawn from a body of knowledge built across many years, tested against many material systems, and now applied to the specific conditions of the tile and bond Avcoat on Orion. Their updated models are good because they are built by people who have spent their professional lives understanding the physics they are modeling. The non-trivial uncertainty in those models is not a reflection of ignorance. It is a reflection of the genuine complexity of the phenomena they are describing. Hypersonic plasma structure interaction over a rough, ablating, evolving surface is among the most computationally and experimentally challenging problems in aerospace engineering. The uncertainty is non-trivial, not because the engineers are inadequate, but because the physics is genuinely difficult to characterize completely with the tools that exist. This matters because the public narrative around the heat shield anomaly has, in some quarters, implied either that NASA made a mistake in choosing the bonded tile approach, or that the subsequent investigation was insufficient. Neither is fair. The bonded tile approach was chosen for sound engineering reasons, and its limitations were not obvious before flight. The investigation was thorough by any reasonable standard. The people conducting it were expert, diligent, and honest about what they found and what remained uncertain. The issue is not the quality of the engineering. The issue is the gap between the quality of the engineering, which is genuinely high, and the quality of the public communication, which has systematically omitted the carefully documented uncertainty that the engineers themselves regard as real and significant. A spacecraft heat shield is, at its most abstract, a bet. It is a calculated, informed, extensively analysed bet that the physics of ablation will proceed in a way that the models predict, under conditions that the models represent accurately, for a duration that the heat shield material can sustain. The bet is made with the best available information. The odds are assessed by experts using the most sophisticated tools available. The residual uncertainty, the part of the outcome that the models cannot determine with certainty, is documented and bounded, and then the bet is placed. The 4 people inside the capsule are the ones whose lives depend on the bet coming out the right way. They know this. They chose this. They are not betting blindly. They are betting with the same information the engineers have, processed through the framework of professional risk acceptance. The public is being asked to understand this bet as something it is not, as a certainty that has been thoroughly established, rather than as a probability that has been carefully estimated. The difference between those two framings is not just a matter of accurate communication, it is a matter of what kind of public accountability the program operates under. A certainty cannot fail in ways that demand explanation. A probability can always be said to have resolved against expectations. And programs that are understood to be dealing in certainties are held to a different standard than programs that are understood to be dealing in carefully bounded probabilities. The honest framing, the one the technical documents support, is the probability framing. The models say the mission will succeed. The models are better than they were before Artemis I flew. The uncertainty is non-trivial and bounded. The margin is positive. The bet is well-informed, responsibly made, and accepted by people who understand what they're agreeing to. That is what certified for flight means. Not that it will certainly succeed, that the probability of success, evaluated by the best available analysis, exceeds the threshold considered acceptable for a mission of this importance and risk level. It means the bet has been placed with eyes open, with the uncertainty acknowledged, with the margin documented, and with the confidence that the engineering community can honestly claim given the tools and data available. That is the true state of the knowledge, and it is more interesting than the resolution narrative. It is more honest. It is more respectful of the people watching the launch, and the people inside the capsule, and the people who built the heat shield. Because it tells the truth about what human spaceflight actually is. The most rigorous and disciplined form of going where you're not certain you can go, with the most careful accounting of the uncertainty that exists, made by people who have decided that the going matters more than the certainty. The instruments being prepared for the Artemis II heat shield, the next generation of thermal sensors, the improved ablation monitors, the enhanced surface photography systems, will produce data that reduces this residual further. After Artemis II flies, the community will know more. The models will be better. The confidence will be higher. And at some point in the future, the phrase non-trivial uncertainty will be replaced in the technical documents by something closer to well-characterized uncertainty with tight confidence intervals. And the gap between the model and the reality will be something the engineers can describe with precision rather than bounds. But that is after. Right now, in the processing facility at Kennedy Space Center, the vehicle waits. The heat shield sits on the bottom of the capsule, 5 meters across, each of its 5,400 AVCOAT cells containing the microscopic voids and permeability characteristics that the root cause investigation documented, the manufacturing improvements that have reduced but not eliminated, the residual variability that the models bound but cannot fully predict. It is the best heat shield that the current state-of-the-art can produce. It has been made by careful people working at the frontier of materials engineering. It has been tested more than any Orion heat shield before it. It has been reviewed by independent experts who found its certification to be sound. And it will experience char liberation events during re-entry that the models say will be within acceptable limits, and that a different set of models, the original set, did not predict at all. The universe is indifferent to the difference between what the models say and what happens. The plasma does not read engineering reports. The gas pressure beneath the char layer does not know what the certification documents conclude. The heat has no interest in whether the margin is comfortable or thin. The physics will do what the physics does, and the heat shield will respond the way the heat shield responds. And somewhere in that response will be the truth about how good the models actually are. We will know after. The sensor data will tell us. The surface photography will tell us. The recovered heat shield, measured and documented by the engineering team in the weeks after splashdown, will tell us whether the models were right, and by how much, and in which direction. Until then, the only honest account of what we know is this. The models say the mission will succeed. The models were wrong before. The models are better now. The uncertainty is non-trivial. The margin is positive. 4 people are going anyway. That last fact is the most important one, not because it justifies silence about the uncertainty, because it demonstrates something fundamental about the species doing this. A species that looks at the gap between what it knows and what it needs to rely on, assesses it as honestly as its instruments allow, and goes forward into the distance anyway. Not recklessly, not naively, with documented uncertainty, understood risk, and the particular kind of courage that belongs not to the absence of fear, but to the decision to proceed despite it. The investigation is not over. It will not be over when the crew splashes down. It will not be over when the Artemis II heat shield is certified. The investigation into how plasma interacts with ablating thermal protection materials at lunar return velocities is a scientific and engineering program that will continue for decades, feeding data forward into the systems that will eventually carry people to Mars and beyond, into re-entries faster and longer than anything attempted today. The question at the centre of that investigation: how much do the models know, and how much do we trust them, and what do we do with the gap between what they predict and what we will eventually observe, is the permanent question of engineering at the frontier. It deserves to be asked in public. The 4 people going to the moon and back are small, the way everyone is small at the scale of what they're attempting. The capsule is small. The rocket is enormous and powerful, beyond ordinary comprehension, and still small against the distance it will cross. The universe is the same size it was when the first humans looked up and wondered what was out there. What has changed is that some of them decided to go, and some of the things they relied on to get there were less certain than the people watching were told. That is the most interesting thing about this moment in the history of the species. Not that we are going to the moon again, but that we are going with the honest acknowledgement, buried in a technical document, present if you know to look for it, that we do not entirely know how it will go. We go anyway. That is the most human thing there is.